Everyone, twisted and as well as a bright fiber optic sensor. This is another type of the sensor. Here in this case, the fibers are twisted, and the same thing is introduced into a material where it has to be tested for the phase difference. As mentioned in the above, the cladded glass fiber loses its optical power from their core under the micro bends. The last optical power and as well as and the micro bend are quantitatively related. See here, when the optic fibers are twisted or braided, the micro bends and the consequent optical losses resulting from the small amount of an ordinary bending of the fiber are magnified. Because of the micro bending and the inherent such as the braid optical fibers can be embedded into any pattern, like either it may be a composite, and thereby the performance is independent of the spacing and as well as the structural fibers. The process of the braiding can be accomplished is as shown in the figure. The first one end of the fiber is fixed to the other end of the fiber and is twisted. After the appropriate amount of the twisting, the fiber doubles on itself and is allowed to braid automatically. For a given length and a type of the fiber is a number of rotation and as well as twist determines the braid and as well as a pitch. See, the braiding mechanism is done by using this method is as shown in the figure. See, one end of the fiber is fixed, the other end of the fiber is free, and that it is anchored through an anchor. The rotating end, once if it starts rotating, automatically the braid or it may be what we can say the twisting, it will takes place. The twisted fiber, the same thing, it can be inserted into the material where the failure or it may be the deformation or the strain is measured. By using this, instead of going for a concept of the micro bend, here what we are using a concept which is nothing but a twisted or it may be a braided structure is used to find out the deformation very easily. The optical fiber as a load bearing element. See, the optical fiber can also be used as a load bearing element and also a load sensing element. The embedded fibers are useful as a sensor merely because of the experience in deformation because of the bond with the structure. The optical fibers are in fact carries the load acting upon the structure. In the experiment reported that the plate is clearly experiencing a large displacement and still the fiber appears to have retained its integrity. Therefore, the question arises in regard the possible of the multifunctioning characteristics of the optical fiber. Why can't they function both as a sensor and as well as the load carrying element, or it may be a member? This question can be answered only through the research program, but the behavioral key element of the contributing for the success is the concept of the diameter of the optical fiber, which is mattering, which is determining the large by the type of the diameter and as well as the cladding and as well as the coating which has been on the optical fiber. The crack detection is one of the basic methods and as well as the basic sensing methods normally by which the optical fiber is having a major application. When the fiber optics strains, sensors experiences a strain along with the structure to which it is attached. Neither sustains a damage in the course of the normal operation, or on the other hand, the optical fiber may be used to detect the localized damage, so it supports the structure. For example, if the same is being embedded it in a composite and such a way that it fails around the surrounding matrix material. One of the possible configuration is as shown in the figure, where the crack in the structural member has led to a crack, and the same thing it can be founded very easily by embedding the fiber into the structure. The development of the crack can be detected by monitoring the intensity of the light transmitted through the embedded fiber, or the light will be lost from the crack in the fiber, and the loss will increases as the crack opening also increases. This reduction in the transmitting of the light will reveals the presence of the crack, but the main problem with respect to this is the location of the crack and identification of the crack at a particular area is very difficult in the structure. Both the existence and as well as the location of the crack can be determined by utilizing a more sophisticated interrogation method. This method is nothing but the optical time domain refractometry, OTDR. This is a very brief pulse of the light sent into an embedded fiber, where it propagates normally until it reaches the crack part, and incidents the pulse and reflected from the crack and travels back towards the input end of the fiber. See, the time taken between the travel from the what we can say the incident and as well as the emerging, that it can be measured, by which at what particular point the crack is, it can be identified very easily. When such reflected pulse is detected, the crack is known to exist. Furthermore, because of the speed of the light in the fiber is known, the time between the generation of the input pulse and the arrival of the reflection can be used to compute the location of the crack. The last part with respect to the fiber optics is nothing but the integration of the fiber optic sensors and as well as the shape memory elements. The sensitivity of the optical fiber to sense the strain in the structure and the ability of the shape memory alloy wire to actuate the offer an unusual opportunity to combine the two in the structural application. A grid pattern of the optical fiber can be visualized, from which not only the strain level but also the location undesirable strains may be established. With this information, the actuation of the structures can be initiated by engineering the corresponding shape memory alloy wire grids, resulting in a smart structures. The aircraft wings, or it may be the bridges, or it may be the buildings, are some of the examples in which the judicious combination of the two technologies by contributing to a greater level of the structural integrity than otherwise is possible. Although this approach is conceptually attractive, the technology need to be developed through the research efforts. The structural weight and as well as the stress concentration are to be balanced against the cost question. The feasibility study are underway, and if the successful, the impact of the design of the smart structure is evident.